Okay, welcome back, everybody. So now we go from divergent continental to divergent oceanic. It's kind of like step three. So these two kind of work together, which is why it's smart to go in that order. So let's look at where we were. So again, picture, here it is like presently rifting. Here it is with a little bit of spreading. Let's go back and look at a long time ago, about 200 million years ago, when South America and Africa would have been together. Of which there's rock evidence for, there's fossil evidence for, there's paleomagnetic evidence for. And this is part of the discovery of plate tectonic theory. Is it really one of the basic ideas was, hey, that kind of looks like it fits over there. That wasn't enough. We'll talk about the whole history of plate tectonic theory. But as it turns out, that was a good guess. So take what would have looked like this about 200 million years ago, rifting, some geothermal stuff, some narrow bodies of water turning into narrow seas, and continue that. Play that forward in your head for 200 million years. Very, very, very slowly. Your fingernail grows faster. Excuse me. Your fingernail grows faster, but given enough time, we've ended up getting this ocean basin that's bigger and bigger and bigger every year. If you've ever flown to Europe or Africa, the next time you got to do it, it's a little further away, ever so slightly. So going back to our sheet here, what does this look like? Let's have on one side our thicker continental crust, which again, really the basic type section for this would put basically the Americas, right? North and South America on one side of this. Thicker continental crust, then on this side is kind of passively attached to the thinner oceanic crust. Way over here on this side, I'm going to do the same thing. Try to line them up best I can. So over here, and again, the typical type section will be, now we're talking the other side of the Atlantic, Europe and Africa. And again, passively attached over here. I'll explain more about that in just a moment. And thin oceanic crust. Until you get out to about halfway where there's this giant ridge. And we draw that giant ridge just as this little thing, but to scale, it's like a mountain range at the bottom of the ocean coming in and out of this piece of paper right here with the entirety of, should have done that in blue, right? Because that's the ocean. The entirety of the Atlantic Ocean sitting on top of it. The mushier asthenosphere down here below. I probably should be a little closer to the middle, but well, forgive me on that if you would. All right, so Google Earth, let's see it. That's it. So the red line. Now there's little green lines on there. Those are offsets. It's not very easy to take a spherical Earth and split it exactly open. On a sphere, it gets complicated. So these little green are transform faults to offset that. Don't worry about transform faults yet. We'll get there. The red line is what we're talking here. That's where the mid-ocean ridge is. If I turn it off, it's like the seam of a baseball. You can see that it sticks right up, and it's tremendous. It's a really large feature. It's like a mountain range underneath water. And that is what we know as the mid-oceanic ridge system. Specifically, this one is called the mid-Atlantic ridge, right? But the spreading happens all right along that line. Okay. Are there others? Absolutely. We'll look at, here's a small one where there's spreading happening right here, and it hits the west coast of North America underneath. I'll put some borders on here for you. Washington and Oregon in the Pacific Northwest. There's, other ones here that go across the whole entire Pacific. This one right here going underneath South America. So let's talk about that passive margin thing. What do I mean by that? On this side of South America, the crust is just like attached. The continental crust and the oceanic crust are essentially passively stuck. That's going to be a whole different ballgame in a minute for your next videos when we look at what's going on this coast where it's active, where there's this plate is coming at this plate and they're mashing into each other, and it creates all kinds of stuff, all kinds of geology going on there. That's going to be our next boundaries we'll talk about in a minute. Here is maybe a little bit more boring. They're just attached to each other and more stable, which is the reason why where we live here in New York and the East Coast in general, we have a lot less earthquakes to deal with. Here's the whole North American plate. The edges of the plate are going to be where the action is. The center away from the edges is where it's relatively safe. So if you picture where you live tectonically on a plate, you live like towards the middle of, I mean, let's assume we live in New York. You currently go to school in the middle of a tectonic plate. And like you might say, I'm an East Coaster, I'm close to the coast, but that's not looking at it tectonically. Look at your world tectonically and say that my nearest boundary is all the way out there or all the way out there. We're pretty far away from them. Therefore, we don't really have to deal with volcanoes and earthquakes the way that active boundaries do. All right. What do you think? Does that do it? Check out our drawing one more time. I think we're good. Mid-ocean ridge system. Maybe we could label that. It's the mid-ocean ridge. And down here would be the asthenosphere. And again, that convection could be pushing out. Passive margins there as these plates continue to spread away from each other. All right. Good stuff. That's it for divergent boundaries. We'll move into the three types of convergent boundaries next. We'll see you in a bit.